We are starting a new unit called Applications of Derivatives. This is day 1 of that unit, and this is your anti-set, so you can pause the video and try to graph these 4 curves that I've given you, trying to spark some memory of what these different curves are going to look like based on what function they are. So you can pause the video and try to graph, and I will explain what's going on here. We have a quadratic function, x squared plus 5, right? This is shifted up 5, so it's going to look like a normal x squared function, but its vertex is going to be at 0, 5, right? This quadratic is in vertex form as well, and it's just been shifted to the right too, if you remember that from pre-calc function transformations. So this has a vertex at 2, 5. You may struggle to remember what x squared plus y squared equals 25 is, but one thing we can think about is that if x were to be 5, y would have to be 0, right? If x were to be negative 5, y would still have to be 0 because 5 squared is 25. So we have 25 plus something equals 25. Well, that something has to be 0. Negative 5 squared is also 25, right? Similarly, if y is equal to plus or minus 5, then x would have to be 0, right? And we'll talk about how that relates to the graph. Here, we have an ellipse with a center at 2, 3. Again, may or may not remember this type of graph from pre-calc. And in pre-calc, we talked about how this meant that the ellipse had a semi-minor axis of 5 and a semi-major axis of 6. Will make more sense when we actually look at these graphs. So here they are. Okay. So here are our graphs. So you can see here we have our quadratic with our vertex at 0, 5, been shifted up 5. This one is shifted over to up 5. This is a radius of, or a circle of radius 5, because again, when x is 5, y is 0. When x is negative 5, y is 0. When y is 5, x is 0. And y is negative 5, x is 0. That ends up forming a circle. Here's our ellipse centered at 2, 3. And we can see that we travel 5 this way, 5 this way. That's our semi-minor axis. And then we travel 6 this way and 6 this way. That is our semi-major axis. Okay, forming this ellipse. Now, not super important that you know how to graph these right now, but today is all about finding the slopes of functions that look like this. So I wanted to start by introducing those graphs. So your next question will be, how do I find the slope of a circle? So 60-second question means that you can pause the video for a second and consider the answer to this question. What would I need to do to find the slope of these lines right here? Right? What would I need to do to find the slopes of these lines? Well, this one's clear. The slope here is 0 because it's totally flat. But how can I find this negative slope and this negative slope? Right? Well, one method would be to actually solve for y, because if we solve for y, that looks more like something that we know how to find the derivative of now, right? So we need to find the derivative and plug in the x value. So in order to do that, we need to first solve for y. So I subtract x squared from both sides. Okay, I square roots, and now I have y equals the square root of 1 minus x squared. So what you can do now is you can hit the boards or do this in your notes. Try to find y prime, recognizing there's going to be a chain rule here because the outside function is square roots, and the inside function is 1 minus x squared. All right, let's look at an answer. Y prime is just equal to negative x over square root 1 minus x squared. Now remember, you would get 1 over 2 times the square root of 1 minus x squared, but then you have to multiply by the derivative of the inside, 1 minus x squared, which would be times negative 2x. And then what happens? Well, the 2's cancel, and then we can put the negative x in the numerator, which gives us this y prime. And now we can figure out the slope at any x value. So let's plug in 0, see what we get. Plug in 0.5, see what we get. Plug in 1, see what we get. Only one of these really requires a calculation. The other two, you can think about what's going to happen. All right, let's check out answers. Okay, So yeah, when x is 0, the slope is just 0. When x is 1, the slope is undefined because we get negative 1 over 0, so it's infinity. And we can see that from on the picture that we'd have a vertical slope versus horizontal in these two different places. And then at x equals 0.5, it turns out it's either positive 0.577 or negative 0.577. And, well, that has to do with the fact that a circle, with a circle you have, every input has two outputs, right? Every input has two outputs. Every input has two outputs. So every input is going to go with two different slopes, and they're just perfectly reflected slopes. And it also has to do with the fact that when you take a square root, you're technically getting a positive and a negative output, like the square root of 4 is plus or minus 2. So there are two different slopes here. But the major point of this lesson is that this looks kind of like a nasty derivative, hard to work with, hard to calculate. And there's actually a way to calculate the derivative without solving for y as we did earlier in this example. So first thing we should consider, okay, what we just did is we solved for y, found the derivative, but is there a way to find the derivative of this? So this is something you should get in your notes. You should get these two examples down, all right? This is called an explicitly defined function, an explicit relationship, because we can clearly see what y is. Y equals this. I can give you an x and you can tell me a y. Explicit relationship. Here, this is implicitly defined because I don't know how y and x are related. I know that x squared plus y squared is 1, but I don't know how exactly y relates to x. Okay, this is how y relates to x. This is the explicit relationship. But that's not clear right here. Their relationship is implicit. So when we take a derivative of a function in this form, it's called implicit differentiation, the title of today's lesson. So let's look at how to do that. Well, I want you to rewrite the example like this because there's actually a little chain rule that's going to happen as we take this derivative. Because what we're going to do is we're going to take the derivative of this curve with respect to x, d dx, of the whole thing. Which means we're going to have to take the derivative of x squared with respect to x plus the derivative of y squared with respect to x, and that is going to be equal to the derivative of 1 with respect to x. Okay, and we're going to talk about how to calculate this derivative. And yeah, I should have put this squared on the outside here. Okay, so let's rethink how we take the derivative of something squared. All right, if we have blah squared plus blah squared equals 1. Well, if we're taking the derivative of blah squared, by our chain rule, it's going to be 2 times blah times the derivative of blah, right? So same thing here, plus 2 times blah times the derivative of blah. And that's just going to be equal to 0 because the derivative of 1 is just 0. It's a constant, okay? So this is the chain rule. This is the derivative of the inside function, and we're taking a derivative with respect to x. And what it means to take a derivative with respect to x is we're saying if we nudge x by just a little bit, how does that affect the other variable we're looking at? Okay, dy dx is ultimately the ratio between a small change in x and a small change in y. And since x and y are related, if we nudge x a little bit, that's going to cause y to nudge a little bit. And what we're looking for is the ratio between those little nudges, dy dx. Okay, that's what dy dx is. But when we take our derivative of this function, right, we have blah squared plus blah squared, right? Well, the derivative of blah squared is 2 times blah. And then we have to multiply by the derivative of the inside function with respect to x. But here's the thing. The derivative of x with respect to x is just 1, right? It's kind of silly. If we nudge x a little bit, well, then how much does x get nudged? That exact amount. If we nudge x by 5, how much did x get nudged? It got nudged by 5, right? It just cancels out to 1. So we don't have to write ddx, or we don't have to write dx dx after our 2x. We don't have to write that part of the chain rule. Okay, so we just write 2 times x. But right here, again, the derivative of blah squared is 2 blah, but then we have to multiply by the derivative of blah with respect to x, right? So How much does y change when x is nudged a little bit? Well, that's what we're trying to find out. That is the definition of the derivative. We want to find dy dx. We can consider this as basically just being a variable right now. We have no idea what dy dx is. We just write it here. But this is the derivative of y with respect to x. That is the derivative of this inside function. The derivative of y with respect to x is dy dx. And this is our part of the chain rule. The derivative of blah squared is 2 blah multiplied by the derivative of blah with respect to x, the derivative of y with respect to x. Okay, derivative of 1 is 0. And our goal is to find dy dx because this is our derivative. This is what we're looking for. So next, if we want to solve for dy dx, we'll just treat it like any other variable. We want to get it by itself, so we subtract the 2x to the other side. Now we have 2y times dy dx equals negative 2x. So think for a second, what should our last step be to isolate dy dx? Well, we are going to divide by 2y to get dy dx by itself. And then now we have negative 2x over 2y, which cancels to negative x over y. This is the derivative of our circle, negative x over y. The slope is determined by x and y. So how can we use this derivative is the question. Well, let's look at this derivative. Okay, as you remember before, I need to undo what I just did here. Okay. As you remember before, we had our derivative that we found explicitly, and we plugged in 0.5 to get a slope, right? Well, now in order to find that same slope when x is 0.5, we'd also have to know what y is. So when x is 0.5, on our curve, we see y is 0.866. We can just divide this and simplify, and that'll tell us the slope at that point, right? If we know x and y, we can just easily plug in and find, whereas before we had to like plug in 0.5 and do all this crazy simplification. It seemed harder, all right? So now we can examine this derivative closer and see what kind of information it tells us. So a question to ask is, what is the x value when y is 0, and what is the slope when y is 0? Well, when y is 0, x must be what? Plus or minus 1, right? Plus or minus 1 squared is equal to 1. So then we can figure out our slope by just plugging in here. We're going to plug in 0 for y. We're going to plug in plus and minus 1 for x. And we get 1 over 0 or negative 1 over 0, which is undefined. And then when, similarly, when x is 0, y is going to be plus or minus 1. But so we're going to have 0 on top, plus or minus 1 on bottom, and that's just going to give us a slope of 0, which would be flat. So let's look at our graph. Okay, when x is 1 and y is 0, x is negative 1, y is 0, we have a vertical slope. But when x is 0 and y is plus or minus 1, we have a horizontal slope. So now we can see how this derivative is giving us a little bit of information about our graph. Where do we have vertical and horizontal tangent lines? In general, if the numerator of dy dx is 0, you have a slope of 0, so we have a flat curve. If the denominator is 0, well, that's an undefined slope, so that must be a vertical slope, okay, an infinite slope. So when a question asks whether you have a horizontal or vertical tangent line, you have to either set the numerator or denominator equal to 0 based on which one it is. Again, numerator 0, horizontal, denominator 0, vertical. So curves start to get crazier. This looks more like an AP level implicit differentiation problem. We have this very implicitly defined relationship. I have no idea how y relates to x. I just know that we add and subtract all these terms, it's equal to 36. But we can still find the derivative and talk about the slope of this curve if we can do implicit differentiation, so you should try that now. Okay, our first step, we just work left to right here. So we say, what is the derivative of x squared, or blah squared, I should say? Well, it's 2 times blah multiplied by the derivative of blah with respect to x, but dx is just 1, so we're not going to write that. Minus, well, what's the derivative of 4 times x? Well, that's just 4 minus 4 plus derivative of 4 blah squared is 8 blah, 8y, multiplied by the derivative of y with respect to x. There's that dy dx, okay, minus the derivative of 40 blah is just 40 times the derivative of blah, so 40 times dy dx, and that is equal to the derivative of, well, yeah, plus derivative of 100 is 0, and that's equal to the derivative of 36, which is 0. And so what do we notice now? This seems a lot harder than my example before because, oh no, I have 2 dy dx's. Okay, so how am I going to solve for dy dx? Because that's what I want. I want to know what dy dx is. I want to know this relationship. What is the slope of the curve? How does a small change in run affect the rise? And what is the ratio of those two, right? That is the instantaneous slope. I want to solve for dy dx. So how am I going to do that? Well, first, notice that we have 2x minus 4 that doesn't have dy dx's, and we have this part that does have dy dx's. So if we want to solve for dy dx, we have to get this red part out of here. So we are going to subtract it over to the other side. So we have subtracted 2x, positive 2x, and we have subtracted negative 4. That gives us negative 2x plus 4. And now we have dy dx, and we have dy dx that we're trying to solve for. Well, it's just like if I were to have, let's say I have 5x squared plus x equals 0, right? Well, this has an x and this has an x, so I can factor out one of those x's. I get x times 5x plus 1 equals 0, right? Well, dy dx is no difference. It's just another variable, so we can factor that out as well. So we're just going to factor out dy dx, and we're left with 8y minus 40. And now, if you want to solve for dy dx, we can just divide this whole thing over to the other side, and we have our new dy dx. And then sometimes a AP Calc question may ask you to simplify this derivative more. So we could say this is equal to negative 2 times x minus 2 over 8 times y minus 5, which would simplify to negative x minus 2 over 4 times y minus 5. Okay, that is the most simplified form of this derivative. So again, the question needs to be, what does this derivative now tell us? What kind of information can we know? Well, first, what you should talk with people around you if they're at the same part of the video as you, or just think about is, when will this function have a vertical tangent and when will it have a horizontal tangent? Think back to earlier in the video. What caused a horizontal tangent versus a vertical? Okay, well, one thing, we know we'll have a vertical if we have to divide by 0. And if we do 8 times 5 minus 40, that would equal 0, causing a vertical tangent. So that happens when y is 5. And if we had negative 2 times 2 plus 4, well, that would be equal to 0, and that would cause a horizontal tangent because that makes the top 0. Now, what the question may ask, though, is not just the x or the y value that causes this, but the actual point. So we can see on our graph that it's at 2, 8, and then also 2, it looks like 2 down here, and 8, 5, and then 8, maybe negative 1 over here. So how can we figure that out if we don't have the graph? Well, we have a function that we can reference. So here we'll come back up here to see, this is our original function that has x's and y's in it, right? So if I'm saying that there is a vertical tangent when y is 5, well, we would have to plug in y equals 5 and solve for x. And if I'm saying that there is a horizontal tangent when x is 2, well, I can solve in x equals 2, or plug in x equals 2 and solve for y. So I would have to say 2 squared minus 4 times 2 plus 4 plus 4y squared minus 40y minus 40y, come on, plus 100 equals 36, right? And what I would have to do is I would have to simplify this and try to solve for y. We're not going to do that now. Usually it's a little bit easier numbers than having like a giant 40y and a 100 and a 36. But the point is, to solve for, if I have y to solve for x, I just have to use the original function. And if I have x and I want to solve for y, again, I have to use the original function. That's how I find the actual point, but this is going to help us find slope. Okay, so holy cow, that was a lot, and this is a hard concept. Believe it or not, we did cover this last year, but it was confusing last year, I know, and it is always a little bit confusing this year too, okay? If you go to the actual PowerPoint, there is a link to a Khan video that will work through another pretty tough example that you can watch. But the biggest thing that we could probably do right now is just after you've gone through this video, you have all your notes down, you've really thought about it, you can step away from implicit differentiation until our next class period, or until your homework assignment at least, and just kind of let it sit for a second, try to process. And this Desmos activity is going to lead you through some some chain rule, tough derivative practice, similar to the stuff we were working with in Unit 1, just to give you some more practice. If you don't finish this Desmos activity, it will be added onto your homework assignment from the textbook, which will give you a little bit of implicit differentiation practice, okay? Again, this was a hard lesson. I would highly recommend you go back through the slides and look at the examples and try to understand what's going on. And then on Monday, we'll touch base again and review implicit differentiation and do some more examples.